Hello, AP Calculus BC students. This is not Mr. Record, but it is Mrs. Morin. And this is your last video for the last set of notes for the year. If you are in AP Bio, you have studied differential equations already. So let's take a look. First of all, in your notes, you have dp dt. This is the differential equation. It is called a logistic differential equation. It describes the growth rate of population, P for population, with respect to time, with a carrying capacity of L. L meaning limit. The carrying capacity has a limit. It says the rate of change of population is jointly proportional. Jointly from algebra meant to multiply. So it is jointly proportional to the size of the population. That's what P stands for. And the difference between the population and the carrying capacity. So this is the differential equation. P meaning population and L meaning limit, which is a carrying capacity. So the solution, if you were to integrate, the solution is this right here. Just memorize this. Okay. The numerator is your limit, and this exponent right here is a negative k times your limit. Okay. A is just another variable, and obviously it's just 1. 1 is 1. So here is a graph that represents your population over time. So your population is increasing over time. But let's talk about the growth rate. Okay, the growth rate, that is a rate, that is a first derivative. As you can see, this piece of your T of t, which is this right here, is concave up. So your growth rate is increasing. Your growth rate is increasing. Let me say that again. So that means its derivative, the growth rate's derivative, is positive. Okay, and then here it's concave down, so your growth rate is decreasing. And right here is halfway in between your limit, L divided by 2. That is when the derivative would be equal to 0. And that is when your maximum rate is going to happen, halfway in between 0 and your carrying capacity. Okay, so here are some things that you need to know. Again, we went through these equations and where L and P are in the equations. L here, P is not in this one. P is over here. So it says the solution to this and the limit as P approaches positive infinity is equal to L. Again, the limit of your population is called carrying capacity. So if dp dt is positive, if your derivative is positive, the population is increasing, right? If your second derivative is positive, your growth rate is increasing. And if your second derivative is negative, your growth rate is decreasing. If your dp dt, that's the derivative of population, is negative, then the population is decreasing toward capacity. And obviously, if your derivative is equal to 0, that's when your population is not changing, and it's a constant. So I did a second derivative sign chart here with what I spoke about. This means concave up. That means your second derivative of population is positive, which means your first derivative is increasing. Your rate is increasing when your second derivative is positive. So that's a review of some things that we've already done throughout the year, but just putting it in terms of population. Okay, what will they expect you to be able to do? Expect to make this look like this, where you might have to factor some things out. Okay, find the limit of your P of t as t approaches infinity. Again, that's just called your carrying capacity. Answer when the growth rate is fastest. The growth rate is always fastest at the half of the carrying capacity. And given A and P of t and dy dt, find K. Is that a typo? I think it is. That should be dp dt. So go ahead and make that change. dp dt. Typo. Okay. All right. Which one of the following differential equations model logistic growth? If the equation models logistic growth, identify the carrying capacity of the model. So take a look. I would stop the video right now. Give yourself a little bit of time to see if you can figure this out. Okay, now I'm going to go over them. So the first one, if I rearrange this and I get dp dt by itself, okay, this right here, this 1, is not our limit because this is p divided by 350. So you actually have to factor out a 1 over 350. When you factor out a 1 over 350, it's like dividing this by 1 over 350, each one of these. And when you divide by 1 over 350, that's the same thing as multiplying by 350. So I just did a little of algebra because I needed to get this p by itself, because I need to make it look like this, p all by itself. So with p all by itself, I know my carrying capacity is 350. And I know that this right here is K times P, which again, we don't really need to know that because they're just asking us to identify the carrying capacity. Okay. Part B, same thing. I'm pulling out the 1 over 1,000 to get the P by itself. Factoring out is dividing by 1 over 1,000, which is the same thing as multiplying by 1,000. So mathematically, this is what you would have left over using your algebra skills, and my carrying capacity is 3,000. Okay, and then the last one, dy dt, which is the mistake that I made, the typo that I made above. Okay. If we were going to have dy dt, then this has to be in terms of y. Just like up here, we have dp dt, and this is in terms of p. So this is not a logistic growth equation. Okay, kind of a trick question. This is the derivative of y with respect to time. Not a logistic growth equation. All right, so example number 2. We have our equation right here. What is wrong with this? Again, you need to have p by itself. Okay, so I'm going to change that to 1 over 1,000. You can keep it as a decimal if you would like. If you need to stop the video, if I'm going too fast, you can stop the video to write these down. But basically, again, I'm going to change it to a fraction because I like fractions better. And I'm going to factor out and get this. And that's my answer. Okay. It says when t equals 0 days, the population is 3,000 grams. So I just rearranged the equation. Actually, it's not my answer. It's just my equation written the way I need to write it. What is the greatest rate of change in bacteria per day? Think about what I said. Greatest rate of change happens halfway to your carrying capacity. Well, what is your carrying capacity? Well, your carrying capacity is 1,000. And the greatest rate of change happens halfway to your carrying capacity, which is 500. Okay? But it doesn't say where does it happen. It says what is the greatest rate of change. So if this is where it happens, and this is the rate of change formula up here, you just go ahead and plug in 500 in for your population, and it will give you your greatest rate of change. This is where it occurs or when it occurs, and this is the actual rate of change. So make sure that you are answering the question. Okay. Again, if I'm going too fast, just stop the video and you can copy these things down. For part B, what are the values of P for which the population is increasing at a decreasing rate? So the population is increasing at a decreasing rate. That goes back to units 5 and 6, I believe. So let's take a look here. Okay. Your population is increasing. Okay. So your population is increasing at a decreasing rate. Again, that is your second derivative being negative. First derivative is positive. Well, we have positive slopes everywhere on here. So this is always happening. And this is happening. A decreasing rate is happening when your rate's derivative is negative, or second derivative negative, which means concave down on the graph. So your answer is from 500 to 1,000. Compound inequality, interval notation, either one of them are acceptable. Okay, example number 3. Again, what is wrong with this? We have to factor this out. We're factoring out a 1/12 in order to get it into the form that we like, so we can see what our carrying capacity is. So let's go ahead and do that. If we factor it out, okay, we get a 12. So our carrying capacity is 12, which is our limit. Okay. Carrying capacity is our limit. That's it. Okay, last one. Write an initial value problem that has a solution of this. Well, we have to go back to the front of our notes and figure out what that means again. 4,000 is your limit. This exponent right here is k times your limit. So you might need to see what parts you need to figure out. So this right here, we know -4 is k times 1,000. So we can figure out what our k is from there. Okay, and so it's asking us to find k times p. So what do we know? We know our L is 4,000. -4, again, going back to the front, -4 is -k times L. So -4 is -k times 4,000. So set up an equation and do a little algebra, which is right here. -4 is a -k times L, and your L is 4,000. So I can multiply both sides by a negative, make them positive. I can substitute in my 4,000, and I can find my k. So here's my k, which goes here. And I know that this 4,000 is my L, so that goes here. So there's my differential equation. And that's it. I hope that makes sense. If you need extra help, you can always visit the AP classroom videos for 7.9. But that's pretty much all you need to know. Don't think too hard about it. They don't ask a ton of questions on these. So there you have it. All right, good job this year, everybody. Good luck on your exam.